And he's going to speak about asset management based on operational availability and life cycle cost optimization achievement, the offshore process case study. The floor is yours.
Yes, thanks. Yeah, my name is Dr. Eduardo Calixto. I'm a specialist in reliability, availability, maintenance, and safety. Yeah, my background is oil and gas industry. I worked by Petrobras in Brazil for 8 years, and then I came to Europe working for some companies in US like Reliasoft, and then worked by Bombardier, different projects also in aerospace by Airbus, and always applying these RUMS subjects. So today, me and Mr. Bolt, Mr. Bolt is from BQR, we developed this methodology and apply for oil and gas, and this methodology can be applied also for different industries. Yeah, so the outlines, starting speaking about BQR and then go through asset management and supporting programs, details, then discussion a little bit how is about the asset performance optimization. Then I show one case study that was a real project. So basically BQR is established in Israel. She has more than 20 years in reliability, safety, and maintenance. So they have 2 divisions. So, and consultant service and software development. They have 3 lines of softwares. Those are feed tracks. This fixed tracks is about the rating reliability for electronics components. They have the care lines that develop all the reliability tools such as FTAs, RBGs, and other models, Markov models. And here that we are discussing today is apmOptimizer, Asset Performance Management Optimization. That's encompasses RUMS and life cycle cost analysis. So that's applied for different industries for all over the asset life cycle. So here's an example for the customer that were applied such methodology all over the world. Okay, so the first concept I started to discuss a little bit about asset management. That main concept is based on the requirements from your customers and for stakeholders. You need to establish your strategy and then define or your performance index throughout the different level of organization. The main question is, first, which programs will support such achievements, such high performance that will be shown in the performance index along life cycle costs. So our colleagues describe all this asset management process. What I'm describing here is the engineering point of view based on application of reliability engineering methods, maintenance methods, and so on. So the first one is a slide that was not my creation. This picture, in fact, this picture was developed for a company in Germany, the Bayer, that's located in Düsseldorf. So they have this concept. Here we can see that the best curve, you have the early life failure, the useful life, and the wear out. So what their concept, if during the asset life cycle, if you are applying correctly different methods along this life cycle, you will not have this early life failure, because during the design, if you apply run analysis, design FMEAs, process FMEAs, RCM, fracas analysis, warranty analysis, and do a very good job during the design, you are able to eliminate the early life failures. And then you have a high performance in your asset during useful life, and also you postpone your wear out phases. So the main point is what you're going to do in each different phase or in your asset life cycle phases along the full life cycle. So the main issue here is you're working 78% with reliability engineering during the design and maintenance, and 30% maintenance here, and vice versa here. Here you work a lot with preventive maintenance to detect failures, to predict failures. But if you are able to develop a higher reliable asset, you don't need to have a higher cost here. You will not have a high cost here. So the second program that's very important in oil and gas is asset integrity management. And this asset integrity management is focused on safety. So for oil and gas, also for different industry, we have unsafe failures that can trigger an accident. And that's one of asset performance targets, risk index, and then in order to achieve also the high performance for your asset, you need to achieve safety high performance. Mostly what we can see that when people discussion about asset integrity management, they focus only in RBI programs, but that's not only the point that you define your inspection. You need to have a real risk management programs, also consider your inspection and maintenance and reliability, and also human factors that can trigger some failures. I will show in a case study what kind of failures can be triggered for human error. The third program is the integrated logistics support, and that is very well applied in the military industry, aerospace, and defense, and that's one application for oil and gas. So basically what we are doing here is to consider, since the concepts, what's our logistic integrated support, what's the effect of logistics in your asset. And then you have one strategy for your logistics and you integrate that in your asset integrity management. Then you are starting to get information from different analysis, life cycle costs, run analysis, level of repair analysis, and so on, and you are able to produce documentation that will support you for the beginning of the operation. So a big problem that we have nowadays in oil and gas is that between the end of design phase and the commission and operational phase, we are not have a program to integrate all this information. And in some cases, we consider run analysis, but that's not so detailed as logistic support analysis. So the proposal is to consider also integrated logistic support analysis. So here, the picture that shows how does it works if you implement in the correct phase different assessments and policies, starting here for the strategy. So you define your strategy for asset management, integrity, integrated logistics support. You define your performance index. You have some benchmarking and technology that you define. And then when you're starting from the concept phase, you're starting to perform some preliminary analysis, such as run analysis, lifetime data analysis, and during the design phase, you go in more details. So in each phase, you need to plan what kind of analysis is critical for your asset in order to achieve performance during operation. So the main point here is that you need to start from the very beginning in the concept phase and then go forward by verification and validation. So if you define some index here, based on such analysis, you are able to verify if the index provided in this phase are good or not, and then you validate that. So usually, what is the concept of optimization? Usually what we have is that we have an asset, so we have different data sources, we have external data and analysis, and we apply some softwares, and then we get some initial input to model, so initial maintenance concept and reliability data. So we input such information in our model, so as Mr. Howell showed today, for example, we have an RBD model to run the Monte Carlo simulation to predict your performance along the time. The main point here is that are you consider the life cycle, the impact of life cycle of your maintenance for all different components. So what you are proposing here is to have different models for level of repair and operation, preventive maintenance, inspection, spare part, and resource. Resource means all the tools and all the people that you need use for preventive maintenance test inspection you consider, and you can optimize in that. You can say, okay, what's the best location for different spare parts or for different teams. So based on it, you are able to achieve your best performance, high operation availability, or lower life cycle costs, and define which are the best time to perform preventive maintenance inspection, which are the best spare parts level, and how many people you need to do that. And then, when you go through that, you have some index and you can predict your asset performance. So what's the idea behind the optimization? So here we have one system with different equipment. So different equipment have different predicted failures. So as we discussed today, we can have an optimal point for each one of them, but the point that you have one system and you need to minimize your life cycle costs. So for each one of them, you need to have a spare ordering What you try to do is optimize your time, your maintenance time, and define which are the best time that you need to put together different preventive maintenance in order to minimize your lifecycle cost or maximize your operation availability. And also define what's the best time to ordering different level of assets. And then you move forward for the future in order to predict. Of course, you need to update it along the time your information about your historical data, and also based on predictive maintenance and test in order to define this optimization. And then you are able to achieve life cycle cost, maximum operation availability, and lower life cycle costs. So here's the concept of optimization. So that's one of objective functions. You want to minimize your expected cost based on a system, based on the system states, the states of time that your system is, and based on decision that you need to have. So subject to each subsystem based on subsystem state on time, decision, and information that you have. So what's the dynamic program do is you have one system, different equipments, or one equipment and different components, and what you're doing is you try to compare your decision, and for each decision you have a cost. So for example, this X11 is a corrective maintenance cost based in a specific time. So that is a specific time, that's a cost. So they compare different possibilities of preventive maintenance and choose the best one here to optimize your operation availability or minimize your life cycle costs. And then they go through another components and it's trying to make a combination. What's the best combination in time to have the best solution for the software? In the software, we have an algorithm that is a logic that you run and give you an answer. And I give you an example in a case study. So basically, that's the offshore case study. Offshore is a system that are studied in the offshore, in the ocean. So you have in the UK, you have in Brazil, we have Indonesia, in different parts of the world, this offshore system. So the scope of this study case is on the subsea. Subsea are the lines and equipment that are under the ocean. So these systems are supplying oil for the platform process this oil, and then you have this oil in the onshore. So basically what's happening here, that's the clients, that was Chevron, they have an assessment program and then define for each supplier that they need to assure the reliability and the performance of their assets. And what we did was support the technique that supply these flow lines, hyzers, to inform and assure that's the high performance. So we apply different methodologies. We apply FEMEA, RCM, RBI, human reliability analysis, lifetime data analysis, run analysis. I will show some of them. This one of the beginning, the first one analysis, that was a FEMEA analysis, failure mode analysis. So here you have a flow line system, you have a different components, so we have a failure modes, you have a phase that such failure modes happen, and here is interesting that you can see that some cause of failure modes are triggered for human error. Human error during installation, barge impact, human error during installation, and some failures on design. This type of equipment have a high reliability unless some human error trigger or deteriorates this equipment and then they fail in the very beginning life cycle, and that's our concerns here. The second important point in here is that whenever we have some severity, here you can see the risk. Here we have severity, here we have occurrence, that's based on risk matrix, and whenever you have a risk or severity in level 3, that's for severity in level 3, you need to include the asset in asset integrity management program. So that's defined by their procedures. So that's why we decided this one, for example, is part of the asset integrity program. In case of unsafe failures, you can have a leakage in the ocean, and that's very critical. So we also perform the RBI analysis based on FEMEA analysis. So here you can see the same failure modes, and for each failure mode, we define during the FEMEA which one we need to have some preventive maintenance, and then we carry out the RBI and RCM. So the RBI was part of asset integrity management, and whenever we have unsafe risk, you need to implement that. So here, for example, you have ROV inspection in each 6 months. So after we discussion, what's the best time, 6 months for 1 year? Okay, here is the run model. So what we've got to get all this information from FIMEA, RBI, reliability data included here in model. We also concern, as I said, integrated logistics support. Here, we concern not only the failures, but okay, if you have a supply with a component here, if there is a failure here, how long you need to transport the component from here to here, how long does it cost? We're considering that. And then we went through the optimization. So that's the case of optimization here. You know that during optimization you have a PF interval, and during this PF interval you need to perform some inspection. So here is the software solution. So when they optimize, the software gives you the equipment that have this signal here, in which time you need to optimizing. And then they also show the life cycle, the total life cycle cost here for each policy. So here is the software solution. So they show you the reliability, the MTBS, operation availability, and then you can make a trade-off analysis between the beginning policy that you have, that was the case A, consider human error, you have an inspection every year, what is the operation availability they achieve, what's the operational cost, and that's the accident cost. So based on an optimal solution, you need to perform inspection for those different components in this time that you achieve a high operation availability, but also a higher cost. So here you have a trade-off analysis, and what do you expect that's achieved between these two values in here. So conclusions, that the optimization model, they do not optimize not only one component, they concern all the components in a system that you apply, and also concern the life cycle cost. So you can apply this model for different set life cycle phases in order to support your decision. In this case, the Chevron, they did not implement this optimization. That was a proposal for us, and they accepted, and now they are implementing their process. So here, some biography, that's my book, the second version of the book. In this book, we have also this case in chapter 8, Asset Integrity Management, and we have a lot of case study for life that I put for FIMEA, RCM, and RBI, and also for lifetime data analysis and other information. If you want some information, I can give you later on. Here is the new book about safety that's focused more on risk assessment, risk analysis. We have different cases in different industry. The last one that I applied was for Airbus in aerospace, but we have for different industry solutions. If you're interested, you can also contact me. So thank you. If you have some questions.
Any questions? No question?
Well, I got one real quick. Kick this off. Hopefully, we'll answer more questions.
Wait for a microphone.
What type of support are you getting for your initiatives?
From?
What type of support, and what do you do? What's the biggest challenges you're finding from leadership? Or
Okay, yeah. In this specific case, the Chevron establish in procedures what they want, and they establish in very details. For example, what kind of analysis you need to provide. Each supplier need to provide them, and then they do not accept any vendors that do not supply this type of analysis. That means their leaders are committed with this program, and is in a procedure in a company, so they support them. For example, during the FIMEA meeting, all the engineers for Chevron and for Technip were in there during the FIMEA. So also the project manager, the engineer leader for the supplier, they were in all meetings to know what they are going to do and what the decision were taking places during the FIMEA. So there are the two types of information that we can see that the leaders support this one, this kind of process. One, they are right procedures. They want assure that the companies that provide service follow the such procedure. And the other one, they attend the meeting, they support the meeting, they make sure that qualified people carry out the meeting and go in there and make this such analysis. So that's a very singular case that is not all like that. We have difficult in different companies that I work that you don't have support from leaders. And if there's not support, they do not see value in such analysis, it's hard to implement asset management and such performance. In this case for Chevron and also for in Germany, for Bayer, in Bayer, for example, in asset manager group, you have a Bayer technology. Bayer technology is all technology, all management that's develop a technology for the Bayer that's the most important for Bayer. And inside this division, they have asset management, performance. And asset management group, you have a manager and you have a reliability engineer manager below the asset management manager and other preventive maintenance. The preventive maintenance have guys from RBI and from maintenance. So that shows that the company really give value for that. But that's not all the cases. Sometimes we are lucky to work with that. In this case, sometimes we need to working hard to convince the leaders and to implement that.
Okay. Thank you, Mr. Calixto.
You're welcome.